Dear students, in this module, I'm going to introduce you to the BLOSSOM scoring matrix. You already know that there are two types of scoring matrices that are frequently used by the pairwise sequence alignment community. So one of them is PAM and the other one is BLOSSOM. So let's take a look at BLOSSOM. So the BLOSSOM scoring matrices were first proposed by Hanekoff in 1992 in one of their papers. So what does BLOSSOM mean? It simply means block substitution matrix. So you look at various protein sequences and you align them and create blocks. And then in those blocks, you count the frequency of substitution between certain amino acids. So block or block substitution matrix requires a block of sequences, as I just mentioned, and you have to perform multiple sequence alignment between them. So you may remember that we were talking about pairwise sequence alignment, or simply alignment between two sequences by sliding them across each other. By multiple sequence alignment, I mean that you can have multiple sequences on top of each other and you can align them by sliding across all the others. We will look at the multiple sequence alignment later, but simply for now, it means that we get similar sequences from the proteins. So how does this block look like? So here is a block that is given for you. So note that in this portion of protein sequences 1, 2, 3, and 4, you do not have any gap. So gaps are not allowed, but of course there may be some mismatches that are here. For instance, G is replaced by an N or S as shown here, as well as some other substitutions. So the only thing that you need to remember here is that in a block only gaps are not allowed. Matches and mismatches are fine with us. So to compute the BLOSSOM matrices, the first thing that you need to do is eliminate similar sequences in the block. That is, eliminate those sequences that are identical in X% positions. So it means that we need to eliminate those sequences and only keep one representative sequence from such sequences which are very similar to each other. So the X% essentially means that 10% similar or 20% similar or 80% similar and so on. So this will help reduce the bias created by similar sequences within the block. Note that if you do not do this, then the scoring matrix will be heavily biased towards the similar sequences. In the second step, you compute the observed frequency of substitution between I and J. So you note this in the aligned pair AI and AJ only. So if one amino acid is substituted by another, you compute the frequency. So Fij becomes the probability of aligning AI and AJ in the selected blocks. In the third step, you compute Fi, which is the frequency of observing AI in the entire block. Okay, so S here is the scoring matrix and Ij is the position I and J in the scoring matrix. So Sij is equal to log to the second base Fij. So note that this Fij was computed here, and Pij, which is computed like this. So you already know Fi and Fj by looking at the observed frequency. So if I equals J, that is the same amino acid, and I is not equal to J means some mutation has occurred and substitution has happened. So you compute Pij like this and you plug it back in and you compute the entire scoring matrix. So the BLOSSOM 62 matrix, or 62 here would be the 62% similarity is computed and shown here for you. So in conclusion, the selection or the choice of scoring matrices can help you to align the protein sequences in very specific ways. And moreover, BLOSUM 62 and PAM 120 are frequently used. So obviously, BLOSUM 62 is better than BLOSUM 50 or BLOSUM 70. You can obviously compute BLOSUM 1, BLOSUM 99, BLOSUM 2, BLOSUM 3, BLOSUM 4 and others, but the sequence alignment community, after a lot of research, has found out that BLOSUM 62 has the resolution to better compare protein sequences and score them appropriately. Note that in PAM-X here, a larger X detects more divergent sequences. So PAM 120 can have a very good resolution as compared to PAM 100. However, for BLOSUM N, that is, we were just talking about N to be 62, a lower N detects more divergent sequences. So if you go to BLOSUM 50, then it will be able to consider much more diversity. But if you go to BLOSUM 72 or 80, then it will not be able to cater for a lot of diversity in the sequences. So as I just mentioned, BLOSUM 62 and PAM 120 are typically used in sequence alignment scoring systems.